All right, so in this video we're going to be reviewing the selection of the resistor voltage, the current limiting resistor for the LED that we used in our last video. I'm going to show you a couple of things for how to measure the voltage drop and explain this whole idea of voltage drop to you. Then we're going to learn how to dim our LED and make it flash at a dimmed state. So this will, and I'm going to show you, we're going to use something called pulse wave modulation to do that, and I've got an oscilloscope that I'm going to show you as well so you can see what pulse wave modulation is actually doing. So we got a lot to cover in this one, a couple of different topics, but I think it will be very helpful for you. So first of all, this page right here that you see that I've got pulled up is Tinkercad. And Tinkercad is a CAD software similar to Onshape, which we've used in our course. I think it's a little bit more basic. It's supposed to be a little bit easier to use than Onshape, but I don't think it's quite as capable in my opinion. I think to do advanced things is easier with Onshape. But Tinkercad does have a free circuit board or circuit simulator that is really good. So I've got a breadboard pulled up here, and I have a power supply, and my power supply is set to 3.3 volts, which is the same as what our Pi Pico and Pi Pico W output on their output pins. It's the logic voltage. And then this big thing up here, all it is just, it acts like a multimeter, which we've used in class, you know, where you can take the two leads and put it on a positive and a negative, and it'll tell you the voltage between 2 points. So I've got that connected right here to the negative rail. So if this is outputting 3.3 volts, we've got the ground or the negative rail, we have the positive, and we should be able to touch this point here and this point here and be able to get 3.3 volts across. So I'm going to start the simulation, and we can see we've got 3.3 volts. So our meter is working, our power supply is working, and they both agree with each other. This is what's giving us the voltage, and this is telling us what the voltage is at these points. Now what we can do is I can delete these wires, and I can draw a wire. This is the negative side here because it's going to the ground on the Arduino Uno. I don't want to do that. I do want to do this. I'm going to connect it to this point here. And, sorry, having a little hard time here. To this point here, there we go, and to this point here. Now, the color of the wires do not really matter, but I'll go ahead and change that. So this is the negative lead. This is the positive lead. So my question for you is, what do you think the voltage will be at these 2 points? So we've got it connected right here, and it connected right here. Think about it for a second. All right, let's run the simulator and see what the voltage is at those points of the circuit. And it's the same thing. If you look here, this is the negative rail, this is the positive rail. Between this negative and this positive is 3.3 volts, right? Well, this wire right here is just coming down, and we're measuring from here. And this wire here is just coming down, and we're measuring from here. So there's no difference, because this is like saying we used a longer wire to connect back to this point. And it's like saying we used a longer wire to connect back to this point. There's no difference whatsoever. So I just wanted you to see that we can measure at different parts of the circuit, and at different parts of the circuit, depending on how we've connected things, it can be exactly the same as what we're feeding into the circuit. All right, so now I'm going to make a change. I'm going to delete this wire, and I'm going to connect it across, maybe. There we go. I'm going to connect it across my resistor. And just so you don't get confused, I'm going to connect this to this end of the resistor. It's exactly the same as what I had it a while ago. I had it connected to this point, but remember all 5 of these pins are connected together. So whether I had it going here or I had it going here, it's all exactly the same. Now, what do you think the voltage will be at this point? Remember in our last video, we did a calculation with Ohm's law, and we said we needed a voltage drop of 1.7 volts and about 10 milliamps, and we calculated that we needed a 159 ohm resistor in order to do that, and we had a 150 ohm resistor, and right here this resistor is set to what? 150 ohms. Well, let's read the resistor band real quick. It's brown, green, brown. This is different than the one that we had because this is just a 3-band resistor. And if we look here, this is how we would read a 3-band resistor. We would see brown, which is a 1, green, which is a 5, and then brown is our multiplier. So we have 1, 5, and then a multiplier of 10. Well, what's 15 times 10? 150. With ours, we had a 5-band resistor, and ours was 150 with a multiplier of 1. So there's different ways to have the resistor have bands, but there's more than one way to get to the same value, depending on the multiplier and the number of bands you have. So we have a 150 ohm resistor here. So our calculation should be close to 1.7 volts. It'll actually be a little bit less because of our resistor value here. So let's go ahead and run our simulation, and let's see what our voltage drop is. And it's 1.32 volts. And it also has a difference to do with this this LED here may have a different forward voltage rating and a different resistance to it. So considering what this resistor, this LED might be, we've got 1.32 volts being dropped across this resistor. So I'm just going to go ahead and write that down. 1.32 volts for our resistor. Okay? Now, let's check to see what our voltage drop is across our LED. So we'll connect it straight to the cathode and straight to the anode. Cathode, remember, is our negative. And let's run our simulation. And the voltage drop across our LED is 1.96 volts. And I think for the one we calculated, it was 1.7 something volts. So this LED is a little different. So 1.96 volts. 1.96 volts for our LED. Now, let's add those two numbers together. 1.32 plus 1.96, 3.28. Those two numbers added together gives us 3.28 volts, or about 3.3 volts. So here's what you need to know. We only have two components in our circuit, a resistor and an LED. If we measure the voltage across that resistor, it has a voltage drop of some amount. If we measure the voltage across the LED, it has a voltage drop of some amount. The voltage drop of all of our components in a series circuit will add up to be the total voltage going into the circuit. So just wanted to show that and explain that to you very quickly. Okay, so we are going to talk about how we can dim the LED on our circuit board. And what you need to know is we're going to use something called pulse wave modulation, or not B, PWM, pulse wave modulation. And what pulse wave modulation is let's say that we have a line that represents 0 volts. And then we have our output pin, which outputs 3.3 volts. Now, I'll draw this in purple. So let's say that we have our LED just on all the time. This x-axis down here is time. Okay? So if we have our LED on all the time, the voltage is always at 3.3 volts all the time. And this is just an on LED. Pulse wave modulation says, let's set a frequency that we are cycling on and off our LED. So let's say that we do it something like 50 hertz. 50 hertz means 50 times a second. So let's say that the end of one cycle is here, and 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 one cycle is here. All right. So if we are going to be dimming our LED, if we want to dim our LED, what we can do is we can say we want to set maybe a 50% duty cycle. A 50% duty cycle means we are going to let current flow through our LED half the time, or 50% of the time. And basically what this is like is, imagine there's water flowing through a canal, and we block the canal up for just a split second and then let the water flow. And then we block it and we let the water flow. And then we block it and we let the water flow. Well, downstream, is the water still flowing? Yeah, it's still flowing. But what's happening is that we've reduced the flow of water downstream because we are blocking it part of the time. And that's kind of a good way to think about what's happening with pulse wave modulation. Because we are not letting current flow half the time, we are reducing the flow of current. And the flow of current is what actually makes the LED light up. So that is going to make the LED more dim, or not as bright. So a 50% duty cycle would look like this. We turn on the LED, and it's on for half the time, and then it's off. And it's off for half the time, and then it's on for half the time, and then it's off for half the time. And then it's on for half the time, and then it's off for half the time. And that continues on and on and on. This would be a 50% duty cycle. Over here, let's say we changed it to a 10% duty cycle. Well, it means that it would be on for 1/10 of the time. Sorry, this is snapping to straight lines. And then it would be off for 90% of the time. And on for 1/10 of the time, and off for 90% of the time, and so on and so forth. So whenever we want to dim an LED with pulse wave modulation, there are two things that we need to set. We need to set the frequency, that is how many times a second how many cycles per second we're going to have. And then we need to set the duty cycle. So I'm going to show you how to do that in our code. So we're going to import from machine another module. or another class called PWM. So from the machine module, we're going to import the PWM class. And what we have here for LED is actually an LED pin. So I'm going to change that to be LED pin. And then I'm going to create a, let's call it a PWM LED. Remember, this is just a variable. I make up the name. I can put anything I want in that variable box, and that's what it becomes. And we're going to create a pulse wave modulation object. And this class provides pulse wave modulation output. And we can see here some example uses. So we can do PWM for a pin, and then we can set the duty cycle for that pin. Alternatively, we can also set a frequency of 5,000 hertz if we wanted to, and so on and so forth. So what we're going to do is we're going to go ahead and use our LED pin, since we already have that set. So it's pin 0 and it's an output pin. And I'm going to set my frequency to be 50 hertz. 50 hertz. So 50 hertz. Go ahead and connect back to my Pico. And there we go. So this is creating a pulse wave modulation LED. Now, if I go ahead and run my code, all right, there we go. So you can see my LED output here. So I'm going to save my code, and nothing happens because I have not set the duty cycle. So in order to set the duty cycle, I need to come in here and I need to set the PWM LED dot duty underscore U16. And this is, I'm supposed to give it an unsigned 16-bit value in the range of 0 to 65,535. And this is a 16-bit value. Now, you need to understand that computers use ones and zeros. So there are two values in a bit, a 1 or a 0, or 0 and a 1. So a 16-bit value means that you take those two options, those two values, and that's raised to the 16th power. So 2 raised to the 16th power is 65,336. But because it is 0 inclusive, then it goes from 0 to 65,535. So if I want to make my LED be on the entire time, then I'm going to do 65,535. And hopefully there my screen comes back. I'm going to reconnect to my Pico. Sorry, having a few problems. Switch over to my there we go. So you can see on my iPhone screen that it is lit up. So if I change this to, if I change this to 0 and save that, jump over here to my screen and then click run the code, it should turn it off because I've set the duty cycle to 0, which means no current is flowing through. Now, this is a 16-bit number, so a 0 doesn't mean 0%. I mean, it does, but 65, 65, 5, 35 also means 100% or on all the time. So an easier way to do it would be just to multiply that number times, let's say, 0.5. And that gives me a 50% duty cycle. So let me show you what I'm doing here in my code. So take that number and multiply it times 0.5 and run it. And it's going to give me an issue. It's going to say a type error, can't convert a float to an int. So if you remember, let me jump down here in my REPL and I'll show you a couple of things. We have different types in MicroPython. The type of anything in quotation marks is an str, a string. The type of an integer, a number one, a whole number, is an int or an integer. And it, again, positive or negative. So type -1 is also an integer. The type of a decimal is called a float. And this 16-bit value that we need to use for duty, for the duty cycle, the duty underscore U16 value needs to be an integer. So we can turn a float into an integer by using the int function, and it drops whatever is on the decimal place. So if I do 1.9, what do you think that's going to be? You might think 2, but it's actually 1 because it's just dropping the decimal place. There is a way to round, but we're not interested in that right now. So all we have to do is come up here and do int and put parentheses around this calculation, and now that should work. So let me jump over to my screen, and I'm going to start decreasing that 0.5, and I'm going to drop it down to 0.1, and I'm going to click save right now and watch to see if you can see the brightness change. And there we go. And it does some weird things with my camera. You can kind of see it flashing, but that has to do with my camera refresh rate. If I was to change this frequency and turn it up to, I'm changing it to 5,000 hertz. Let's see what happens with the flash that you see. So I will save that code and run it. And that gets rid of the flicker because we've increased the rate at which it is updating the cycles, how many times it's updating a second. So I'm going to change it back to 50 just so you can see that, and click run. Now I've got an oscilloscope down here, and I'm going to auto range my oscilloscope, and it's going to lock in on those square waves. And we can see that it says that it has a duty cycle of 10% with a cycle length of 20 milliseconds. And if we look at our code, I currently have a frequency of 50 hertz. Well, how many milliseconds would be in one cycle if you're doing 50 cycles per second? Well, you just take 1 and divide it by 50, and that gives you 0.2. 0.02. So that is 20 milliseconds. So milliseconds, remember, is to the thousandth. So 0.02. So that makes sense then why our... Yeah. So that's why we have 20 milliseconds showing right there for the cycle. Now our duty cycle of 10% is what we put in here. We put in times 0.1. So we're doing 10% of 65,535. So let's do it to 0.5. And I'm going to jump back over to my screen, and then I'm going to send my code so you can see the oscilloscope and the brightness change. So I'm going to click send now, and boom, you can see the LED got brighter. With my eyes in the room, I cannot see it doing any of that pulsing, flashing. So you see that through the camera because the camera is able to see faster than my eye can. But if you were in the room, you could not see that it's flashing. Remember, if I turn up the frequency, that goes away and it looks exactly the same as it does on the camera as it does to my eyes. But the big thing is, notice we've got that square wave, exactly like what we were talking about, where it's on. Each one of these boxes is 5 milliseconds. So we've got a total of 4 boxes is 20 milliseconds. So it's on for 2 boxes, so it's on for 10 milliseconds, and then it's off for 10 milliseconds. That is, it's 50% of the time it's on, 50% of the time it's off. It has a duty cycle of 50%. So, wanted to use this oscilloscope to show you what's actually going on with the pulse wave modulated signal. Now, let's make our LED flash off and dim, off and dim. So the way that I would do that is jump back in so you can see the code. I'm going to do a while true loop. While true. I'm going to tab that over. We're going to set it to 0. Sleep for a second. And then let's set it to be only 0.1% or 0.05%. Let's just do 5%, so 0.05. 0.5 would be 50, 0.05 is 5. All right, and before I click run, let me jump over so you can see what's going to happen. And let's run our code. Oh, I forgot to do an important step. I forgot to sleep here. There we go. Now I'll run it, jump back over so you can see what's going on, and it's flashing I don't see on the screen. You see like it's getting brighter and then dimmer, brighter and then dimmer. All I see is on for 5%, off, on for 5%, off, on for 5%, off. And you can see exactly what that's doing with the duty cycle and the 20 milliseconds for the cycles. It's giving 3 volts every time it's on. Each one of these boxes is 1 volt, and it's up here right at 3 volts, so 1.5 of these boxes. Or excuse me, each one of those boxes is 2 volts. So it's 1.5 of those boxes. That's 3 volts, and you can see it's cycling on and off with that duty cycle. Letting a little water flow, no water. Little water, no water. And that's giving us a reduced brightness with our LED. All right, so that's going to be an important lesson for us whenever we move on to controlling servo motors, but also future for dimming LEDs is understanding pulse wave modulation. So what I'd like for you to do is to create a loop that is going to, similar to this, flash by adjusting the amount of time that the microcontroller is giving current to the LED through setting that duty cycle. All right, I'll see you in the next video where we'll talk about servo motors and how to control those.